Morning to each and everyone. Today I'll be discussing the geometric pattern, symmetry and isometry. Here are the objectives. Geometric patterns appear in many areas of mathematics like art, nature, and architecture. Symmetry and isometry are fundamental concepts in understanding how these patterns are formed and repeated. This presentation can explore the roles of symmetry and isometry in geometric patterns. What are the geometric patterns? A geometric pattern consists of shapes that repeated in a regular structural way. These patterns can be observed in nature like flowers, petals, man-made objects like tiles and or wallpaper. Which means that geometric patterns are created by regularly repeating shape in a structural way. These patterns are found both in nature like flowers, petals, and human-made design like tiles and wallpaper. Like for example, snowflakes, tessellation, and tilling patterns. That would be all. Thank you.
Good day everyone, I'm Marmolis Dayo, and today I'll be discussing symmetry. Have you ever stopped to wonder what makes certain things look perfectly balanced or visually pleasing? What if I told you that the answer lies in a concept called symmetry, which plays a vital role in the beauty of nature, art, and even the designs around us? Symmetry is a concept that refers to the balance and proportionate arrangement of parts or elements within an object, shape, or pattern. It means that an object can be divided into sections that are identical or match in some way. And the fascinating part? These objects can be transformed whether by rotating, flipping, or scaling and still maintain the same appearance. In much simpler terms, symmetry is about harmony and order in the world around us. It's a fundamental principle in mathematics, science, art, architecture, and nature. Symmetry helps create balance, functionality, and patterns that are predictable and visually appealing. So for example, if you fold a butterfly in half, both wings are reflections of each other. This is reflection symmetry. The pattern on a flower might remain the same when rotated slightly, which demonstrates rotational symmetry. The rotating arrangement of leaves around the plant stem shows transitional symmetry. So, symmetry isn't just about what we see. It also applies to forces, motions, molecular structures, and even the vast universe. It's a way to understand how the world maintains balance and consistency, both in nature and in human-made systems. Now, there are different types of symmetry, just like I have mentioned earlier, like reflection, rotational, and transitional symmetry. But my groupmate Miss Piniflor will be dividing deeper into those symmetries. So, thank you.
So let's proceed to types of symmetry. Number 1. Reflection symmetry, also known as mirror symmetry. This occurs when one half of an object is a mirror image of the other. A classic example is a square. If you draw a line through its center, both halves look identical. Number 2. Rotational symmetry. This type exists when a shape can be rotated around a central point and still appear the same at a certain angles. For instance, a 5-pointed star aligns perfectly every 72 degrees. Number 3. Translational symmetry. This occurs when a pattern can be shifted in any direction without changing its appearance. Wallpaper designs often exhibit this symmetry, maintaining their look even when moved.
So what is isometry? Isometry refers to the transformation of an object that preserves the same shape and size of an object. This means if you're applying the isometry to an object, the resulting object will be congruent to the original object. And we will be discussing about the three types of isometry. These are the translation, reflection, and rotation. But before that, I just want to remind you that isometry, the angle, the side, the measurement, and the size of an object will remain. Now, we will be discussing about the three types of isometry. First is the translation of what we call the slide. So this type of isometry, the translation, is the moving of an object without changing its size and shape. So you are moving an object to a place to another. However, there are no changing happens between an object and it remains the same size and shape and nothing will change it. We'll be discussing about the rotation. The rotation is turning an object around the point. So there is a point or what we call the point of rotation. So in the point of rotation, an object can be moved or inside or outside the turning point of an object. And last one is the reflection. So reflection is flipping an object around the line. So the line is what we call the line of reflection, which help us to determine the measurements of an object.
I will be discussing the concept of symmetry and asymmetry, their differences. So let's start with symmetry. Symmetry refers to the inherent property of a shape or design where parts of the pattern correspond to each other in a balanced way. A symmetrical shape remains unchanged when divided or reflect along a specific axis. A great example of symmetry is a butterfly wings. If you draw a line down the middle of butterfly's body, the left and right wings are mirror image of each other. This is called the reflectional symmetry, where one side is an exact copy of the other. When folding along a central line, the butterfly itself does not move or change. It simply as a balance of structure. Now, let's move involves a specific transformation of an object. This transformation includes translation, rotation, and reflection, but no matter how the object moves, its original size and shape remain unchanged. A good example of isometry is a rotating triangle. A triangle drawn on a piece of paper. If I pick it up, rotate it 90 degrees, and place it back down, it still has the same shape and size. It hasn't been stretched or altered. This is an example of rotational isometry because the object undergoes a transformation, but it keeps its original form.
A butterfly is an example of reflection symmetry, as its wings are mirrored on the other side when folded along a central line, meaning it exhibits a bilateral symmetry where other half is the reflection of the other half. When we say bilateral symmetry, it is another term for the reflection symmetry. Snowflakes are prime example of rotational symmetry, meaning you can rotate snowflakes by a specific angle and it still look like the same. Essentially, it has 6-fold rotational symmetry. Snowflakes are based on hexagonal shape, which naturally has 6 lines of symmetry, allowing for rotation of 60 degrees intervals. If you imagine spinning a snowflakes on its center points, it will appear identical at every 60 degrees rotation. Tiling patterns and translational symmetry are closely related concepts, where tiling patterns demonstrate translational symmetry by repeating a single unit across a surface without gaps or overlaps. Another example for translational symmetry is brick walls, checkerboard, and also the wallpaper with repeating designs.
Isometry refers to the process of transforming geometric shapes in a way that maintains their size and properties. This can include translation, moving a shape to a different location without changing its size or orientation. Rotation, turning a shape around the point while keeping its shape the same. Lastly is reflection, flipping a shape over a line while keeping its size and proportions the same. These transformations do not change the shape of the object, but rather change its position or orientation in space while preserving its size and features.
Hey everyone, my name is Rizabel Kindamalinas and I'll be tackling the real-world application of symmetry and isometry. Examples of symmetry and isometry in real-world application: the art, the nature, the architecture, and technology. For art, there are 2 examples, which is the Renaissance paintings and the modern abstract art. The best examples for Renaissance paintings is the Last Supper and School of Athens. The Last Supper is artist by Leonardo da Vinci, and the School of Athens is artist by Raphael. So the Last Supper and the School of Athens, they are a symmetrical balance because of they are both same numbers of each side and also 1 in the center. So that is an example of symmetrical balance. Another one is the modern abstract art. As you see in the picture, it is an artist by or an artwork of Piet Mondrian. As you see in the picture, they are consist of colors, which is the red, the yellow, and the blue ones. So that is an example of symmetrical balance because of the colors and also the shapes. And another one is nature. Nature, an example of nature is the starfish, the flowers, and the animal bodies. For flowers, they consist of two symmetry, which is the radial and bilateral symmetry. For radial symmetry, an example for this, the roses, as you see in the picture, which is the flowers that you can see for radial symmetry. And for bilateral symmetry, is for an example for this is snapdragons, the orchids. So that is an example of bilateral symmetry. And another one is for architecture. Architecture is they have 2 examples, which is the Parthenon Greece and the modern skyscrapers. For modern skyscrapers and the Parthenon Greece, as you see in the picture, that is an example of architecture and real world application of symmetry and isometry. They have a balanced symmetry and they have also a balanced isometry. So another one is the technology. Technology consists of isometry and symmetry. It is because an example for this is the CGI characters, which is the computer generated imagery. Because computer generated imagery consists of 3D image. So that is an example of isometry. Conclusion: symmetry and isometry are powerful tools for understanding and creating visually appealing and functional geometric patterns. They provide a framework for designing and analyzing shapes and structure, and these principles are fundamentals to both the aesthetic and structural qualities of designs. Spanning from natural forms to architectural structures, they are not merely decorative elements but contributed to the overall functionality and stability of objects. Appreciating how symmetry and isometry functions enhances our understanding of the world around us. By recognizing these patterns, we gain a deeper appreciation for the underlying order and design principles present in nature and human creations. In essence, my topic connect the abstract mathematical concepts of symmetry and isometry to their tangible applications and broader significance in the world around us. They illustrate how these concepts are not just theoretical construct but powerful tools with wide-ranging practical implications.